So this is section 6.5. We're talking about trigonometric form of complex numbers. All right, and just a quick reminder. We'll do more with complex numbers second semester, but just a quick reminder what we're talking about with a complex number. A complex number we say z is a plus bi, where a and b are real numbers, and I is the square root of -1. And one important thing to remember is that I squared equals -1. So a complex number is a number that we can write as a plus bi. So what we're going to do is we're going to treat complex numbers almost like we treated vectors. So what we're going to do is make a coordinate system where instead of the y-axis, we have the imaginary axis. So we call the y-axis instead of the y. When we're talking about complex numbers, we call this axis the imaginary axis, and the x-axis we call the real axis. So if we plot a number a plus bi, we're thinking that the real part is the part without the I, without the imaginary number. So when we plot this is like plotting. We plot the point a comma b. So we're going to go over a units and up b units. So this point would be a plus bi, where we're down here a on the real axis and we're up here b units on the imaginary axis. So we go over a and up b. That's what this is telling us. So we look at this just like we looked at a point, or just like we looked at a vector. If we thought of this as a vector, it's the same as we treated the vector AB. We go over a units and up, left or right a units, and up or down b units. So it's the same idea as plotting this vector. So when we're plotting an imaginary number, we're just thinking of plotting a vector or just plotting the points a comma b. To find the absolute value of a complex number, so if we have z is a plus bi, that's our complex number. The absolute value of z, we can also write the absolute value of a plus bi, and we find the absolute value of a plus bi the same way we find the absolute value of the vector, or the magnitude of the vector ab. It's just the square root of a squared plus b squared. So again, we're treating this, we're almost visualizing this complex number as a vector, where a is the x component and b is the y component. Well, here instead a is the real component and b is the imaginary component. So we find the length or the absolute value the exact same way. It's the same idea. So if we wanted the absolute value, just to do a quick example, the absolute value of the absolute value of z equals 4 minus 3i. So all we need to do here is take the absolute value of 4 squared plus negative 3 squared, which gives me the square root of 25, which is just 5. And this is exactly like we did with a vector. If we thought of this as a vector, it's exactly like the vector 4 comma negative 3. The absolute value or the magnitude of that vector is the square root of 4 squared plus negative 3 squared. So it's just like finding the magnitude of a vector. And if we're looking at our point here, what we're doing is we're making a right triangle. If we connect this, make this the hypotenuse of the right triangle, we're finding the length of the hypotenuse of this right triangle, essentially. This all comes from the Pythagorean theorem. So to find the absolute value, it's just like finding the magnitude of a vector. You just take the square root of each component squared. Make sense? Questions on that? All right. So this is this is the basic idea of plotting an imaginary number or a complex number. Thinking of we call this the complex plane. So we have our imaginary axis, our real axis. Well, now we know a little bit about angles. We know a little bit about trigonometry. So we can use what we know about trigonometry to work with this complex number as well. So that's what we're going to do next. So we want to look at the trigonometric form. So I'm just going to call it the trig form. So we're going to do just like we did the other day with vectors. We're going to look at this just like we did with vectors. So I'm going to draw my axes, my real axis, my imaginary axis, like we did before. So there's my imaginary axis, there's my real axis. All right, so there's our imaginary axis and our real axis. We're going to plot our number here, a plus bi, and we're going to draw a segment from the origin to our point. So here's our segment. And we're going to turn this into a little right triangle. So here's this side of my triangle, down like so. This length is A, this length is B, and we're going to call this angle theta. And the length here, the hypotenuse, we're going to call r, like a radius. So on this right triangle, the radius is the hypotenuse of this right triangle. So r is the square root of a squared plus b squared. R is our magnitude, or our absolute value of our complex number. So that's just the hypotenuse of this little right triangle. And we can say that A from this right triangle equals r cosine theta. That's the length of this side of our right triangle. And B equals r sine theta. So rather than writing this as a plus bi, I can write this. I can write if z equals a plus bi, I can write this as r cosine theta plus r times I sine theta. So I'm just rewriting the a and the b as the sides of this right triangle. And usually what we do with this complex number is we say, we factor out the r, since r is common. We say this is r cosine theta plus I sine theta. So that's the trigonometric form of a complex number. And it's all just based on this little triangle. We think of this point, a plus bi, as this point in the plane, the complex plane. We can draw our little right triangle like so, and we can rewrite this point as r cosine theta plus I sine theta. We call r, this radius or this length, the absolute value, however you want to refer to it, r is called the modulus. R is the modulus of z. So the modulus is just another word for the absolute value. And theta is called the argument of z. So our absolute value, or the length of this hypotenuse, is the modulus, and theta is the argument. And based on our right triangle again, yes? Oh. So if we look at our right triangle here, we can see that the tangent of theta is b over a. So just like we did with vectors, where the tangent of our angle was the y component over the x component, in this case, tangent is the imaginary part over the real part. So if we're given, we can figure out from the standard expression for a complex number a plus bi, we can figure out our theta, and we can figure out the modulus, which is just the same as the absolute value. So again, this is really very, very similar, almost exactly the same as what we did with vectors the other day. Any questions so far? All right, let's look at a quick example of working with the modulus and the argument, and then we'll talk about how we multiply and divide complex numbers in trigonometric form. All right, so let's look at an example. So we want to write 4 cosine 5 pi over 6 plus I sine 5 pi over 6 in a plus bi form. So for this particular problem, all I'm going to do is either from the unit circle, or you can use your calculator. We're going to calculate cosine of 5 pi over 6, the sine of 5 pi over 6. So I'm going to rewrite this as, if I'm going to say, I'm going to write this z equals. So I'm going to say z equals 4 times the cosine of 5 pi over 6 is minus square root of 3 over 2. plus I, and the sine of 5 pi over 6 is 1/2. So I'm just writing this, just finding the sine and the cosine of 5 pi over 6. And then I'm going to distribute the 4, and I get minus 2 square root of 3 plus 2I. And if I wanted to go the other direction, if I were given this form, to go the other direction, I would say tangent of theta. If I'm going in reverse, I would say tangent of theta is b over a, 2 over negative 2 times the square root of 3. So tangent theta is minus, if I rationalize this denominator, square root of 3 over 3. And on my unit circle, I would say, where is a tangent of theta? Square root of 3 over 3. I know that the x part, the real part, is negative, and the imaginary part is positive, so I have to be in the second quadrant. So I would look for a second quadrant angle that has a tangent of negative square root of 3 over 3. And to find my r, my modulus, from if I were given this information, r would be the square root of negative 2 square root of 3 squared plus 2 squared. And when I simplify that out, I would end up with my modulus of 4. So working the problem this direction, I'm just finding the sine and the cosine of my angle. Working the problem in the opposite direction, from the imaginary part and the real part, I find my angle, and I can find my modulus by finding the absolute value. Questions? All right. So what the one thing that we're trying to do is write all of these, write the complex numbers in trigonometric form. But it turns out that trigonometric form gives us a convenient way of working with complex numbers. I don't know if you remember, if you think back to what you did in Algebra 2, when you multiplied complex numbers, you had to FOIL, and then you had to remember that I squared was negative 1, and then to divide complex numbers, you had to multiply the numerator and denominator by the conjugate and simplify. So it wasn't not necessarily difficult, but there's a lot of work. It turns out that writing complex numbers in trigonometric form makes multiplication and division of complex numbers very easy. So let's look at how that works. So multiplication and division. Oh, and just as a quick note, trigonometric form of complex numbers, another way of referring to that is polar form. So trigonometric form and polar form, you'll see them used interchangeably. They mean the same thing. All right, so what we're going to do is we're going to multiply two complex numbers written in trigonometric form and simplify the result, and we come up with a nice formula. So let's say that Z1 is R1 times cosine of theta 1 plus I sine theta 1. So we just have one complex number, and Z2, some other complex number, is R2, some other modulus, times the cosine of theta 2 plus I sine theta 2. So we're going to multiply these two together and simplify what we get, and it's kind of nice how it turns out. So Z1 times Z2. I'm going to write this all out. This is going to be R1 cosine theta 1 plus I sine theta 1. And we're multiplying that by R2 sine theta 2, or sorry, cosine theta 2 plus I sine theta 2. Now I can, since R1 and R2 are just multiplying these parentheses, I can pull those two out. So I'm going to write this as R1 times R2, and then I'm going to FOIL these inner parentheses. I'm going to FOIL all of this out. So when I rewrite that, I get cosine theta 1 cosine theta 2, that's my first. My outside is plus I cosine theta 1 sine theta 2. My inside is plus I sine theta 1 cosine theta 2. And then my last is plus I squared times sine theta 1 sine theta 2. So I get this long, complicated thing. Well, I'm going to put the real parts together and the imaginary parts together, and remembering that I squared is negative 1. So I'm going to rewrite this as this equals R1, R2. I'm going to put the real parts together, the parts without the i's together, and the parts with the i's together. I get cosine theta 1 cosine theta 2. I squared is minus 1, so I get minus sine theta 1 sine theta 2 plus I times cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Now, does this cosine theta 1 plus cosine theta 2 minus sine theta 1 sine theta 2, does that look familiar? Thinking about some identities that we worked with in our last chapter. It's a cosine sum formula. So this is R1, R2 times cosine theta 1 plus theta 2 plus I times, and this formula is the sine sum formula, plus I sine theta 1 plus theta 2. So we've turned this long, complicated thing into something that's a lot simpler. But look what we've done. To multiply our complex numbers, we multiply the modulus and add the angles. So we're multiplying the modulus and adding the angles. So that's what this, in trigonometric form, to multiply our two complex numbers, all we have to do is multiply the modulus and add together the angles and rewrite them in trig form. So we and I'll use the plural, multiply the moduli, that's the plural of modulus. Multiply the modulus, add the angles. So this gives us a really convenient way to multiply two complex numbers. If I have them written in trigonometric form, all I have to do is multiply the modulus, the moduli, and add the angles. And I'm not going to go through the division, but it's the same idea. I can divide the two complex numbers, use a trig identity, and I end up that z1 divided by z2 is r1 divided by r2, and I subtract the angles. Cosine theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. So to divide complex numbers in trigonometric form, I divide the moduli and subtract the angles. So in trigonometric form, we can simplify this process of division and multiplication because we just end up multiplying and dividing real numbers and adding or subtracting the angles that are our arguments. And this all comes from because we can represent these, once we multiply these out, with our trig identities that we worked with in our last chapter. Questions on that? All right, I just want to do one example of multiplying and dividing, and then we'll be done. So for our example, we have Z1. Our complex number in trigonometric form is 8. Cosine, thank you. We have 8 cosine 120 plus I sine 120. So there's our trigonometric form, and Z2 is our second complex number is 6 cosine 150 plus I sine 150. We want to find Z1 times Z2 and Z1 divided by Z2. So we're going to do Z1, Z2, and Z1 divided by Z2. So Z1, Z2, multiplying these two together, equals, we're going to multiply the moduli. 6 times 8 is 48, and we're going to add the angles. Cosine of 120 plus 150 is 270, plus I sine 270. And if we wanted to write this in a plus bi form, in our standard form, the cosine of 270 is 0, and the sine of 270 is -1. So this turns out to be minus 48i. Because the cosine of 270 is 0 and the sine of 270 is -1. And if we do Z1 divided by Z2, we divide the moduli. So we get 8 divided by 6 times the cosine of 120 minus 150. So we get the cosine of minus 30 degrees plus I times the sine of minus 30 degrees. And I'm going to reduce this. This is 4/3. The cosine of minus 30 degrees is square root of 3 over 2. And the sine of minus 30 degrees is minus 1/2. And I'm going to distribute, so I end up with 2 square root of 3 over 3 minus 2/3 I. And I'm missing one parenthesis. There we go. So writing our complex numbers in trigonometric form simplifies multiplying the numbers and dividing the numbers. If you ever go any further with complex numbers in trigonometric form, finding the roots, the nth roots, And finding the powers of complex numbers is very, very easy when we write them in trigonometric form. And in fact, if any of you ever go further with math or science, if you get a chance to take a class in complex variables, it was really one of the coolest classes I ever took when I was at college. It's really such a different way of looking at numbers and at math. It was one of the most interesting math classes I ever took was in complex variables. If you're interested at all. All right, any questions? Okay. Homework. We got 20 minutes now. You can finish. I don't know why I wrote this way, but I'm just going to keep it this way. Maybe that was supposed to be all. How do I do this? There you go. I don't know why I wrote it this way. Okay, there you go. There's your homework.